Started. Welcome everybody. Thank you for coming out and coming to listen and learn about Scala 3. Thanks to Nick for the presentation, for the invitation to come, and especially to Spendit for hosting me tonight. I'm going to start with a question. How many people have visited London at some point? About half, maybe, yeah, about half of you. You may be familiar with this famous symbol from the Underground, and you might be wondering why it is the cover slide for my presentation. You maybe have seen the map of the London Underground. Even if you've never ridden on the trains, it's quite big. There are I think over 250 stations. And what I would like to do today is build a small command line tool in Scala 3. So this is a greenfield project, no migration from a Scala 2 version. We're starting afresh with something completely new to use the API that's provided for free by TfL, Transport for London, to query various data about the Underground network. So I hoped this would be possible to build, go from nothing to a working application in the space of about 45 minutes. I prepared this for a talk I did remotely in Dallas a week ago. And I realized on the day I was presenting that actually 45 minutes isn't enough to go through everything. So what I will do is I will show you the interesting parts of the development. And I'm going to do this in possibly a quite novel way, because I can't live code it. Typing that much code precisely without mistakes is going to be too difficult for me. So what I've done is I've created a Git repository, which you can look at either now or later. It's my GitHub account, propensive/tube. We're going to call this little application tube. And that repository has been carefully crafted with over 250 commits, each one a tiny modification to the code that will add small fragments piece by piece to go from nothing, from a hello world application to a fully working command line tool. And I will show you in VS Code a few things going on at the same time here. On the left-hand side is the code we're working with. This is what we're starting with. This is a very typical hello world application in Scala 3. At the top right is SBT, which is running continuously. It is going to build and compile the code on the left whenever it changes. And down here is a little tool, little script I wrote, which is called nav, which is mainly for my benefit in presenting to you, but you can also use it yourselves if you clone that repository. And this will show me a commit. So highlighted there is the very first commit, C07E09D. This is the commit that introduces the Hello World application. And if I press the arrow key to go right, you will see that there was a small change there, which adds this line to import Soundness. When I did that, SBT jumped into action and rebuilt everything. And we're now on commit 1, which has just added the Soundness import. Above this is a small diff to the previous commit. Below is a small diff to what is coming next. So my plan for today is to navigate through this step by step, tell you what each little change is, show the more interesting ones, and give you insight into a few things. One, what it's like to program in Scala 3 on a greenfield project. And this isn't just a greenfield project. This is a project that will be built on a set of libraries I've been working on for the last couple of years, which are collectively called Soundness, but each one is that there are many libraries with separate names that you can look up later. But these libraries have been built from the outset for Scala 3. They don't work on Scala 2. They were never designed to work. They were designed to use all of the wonderful new features that are only possible in Scala 3. I don't want to spend a lot of time explaining how you can become an expert writing code with Soundness. that's beyond the scope of what is possible tonight. But I am going to give you, I guess in some sense it's a deep dive, because we're going to go from nothing to a full application quite quickly in the space of less than an hour, I hope. But it'll also be very broad, because you will see lots of different libraries, lots of different types of code, and lots of features of Scala which you've possibly never seen before. So while I'm going, I'd like to invite questions. If you see something that you just don't understand, just raise a hand, and you're probably not the only person who's spotted it, and I will happily explain. If it does make sense, don't say anything, and I will just keep going. What I'm going to do is start by proving this is a working application. I'm going to briefly leave SBT's continuous compilation and type run, and here you can see that hello world is output. This is what we would hope for. So let's jump back there. And yeah, hello world is what you get if you start from commit 0. Now, from commit 9, if I jump forward, you can see a few changes. Now, it's going to take me too long if I explain what all of these are. But I have modified this from a standard Scala 3 application to a Soundness application, which adds a little bit of type safety. It puts some constraints on what we can do. First of all, we wrap it in a block called application, passing in, we're actually going to ignore the parameters, so we write nil there. One thing you have to do is return an exit status. When you run an application, we sort of assume it's going to be okay unless an exception is thrown, but here you must be explicit about it. That's a requirement of the definition of application here. We're also printing some output, and we're using this E interpolator just above the pointer there, which is going to take advantage of control characters in the terminal, and it's going to make hello world appear bold and italic. And there's some other little differences, like using out.println instead of just println, which makes sure that we are explicit about where we are sending the output to. And there's just up here, there is a specification, a declaration, in fact, for which standard input-output source we're using. We're using the virtual machine's input-output. We are clear about that by this import here, and you will see this is a bit of a theme. Imports are used for declarative programming. Imports are valid within a certain scope. In this case, it's the entire file, but we take advantage of the fact they are scoped to apply a single setting or declaration to that entire scope, which means we don't have to repeat it with every single call. It's a very convenient way of scoping certain common parameters or frequently used settings. So that has compiled. If I switch over to a console, hopefully this is visible. We should see that in the target Scala 351 folder, we have just up here, it's not visible on my screen actually, nor yours in fact, but it's just there is tube.jar, and we can run that with java jar tube dot, actually I need to be in target Scala 5 tube.jar. It is a runnable jar and hello world appears, but now it's bold and italic. Okay, it does what we wanted it to. So what comes next? A little bit further on commit 14. And this sort of shows you the number of changes, number of incremental changes you need to make to get from one version to the next version. And if you want, afterwards, you can go back and look at each individual change and try and understand what they did. I will jump through straight to number 14 by just doing this. And now we have there's a couple more imports here. And application has changed to CLI. But the rest of this is almost the same. We're printing the arguments. The arguments no longer have to be passed explicitly. They are simply available as a thing called arguments in this scope here. Now, why have I changed from application to CLI? Well, we are building what I call a daemon command line interface application. So with most Java applications that run on the command line, you run the command, it starts a new JVM, it does all sorts of startup setup, it does what you asked it to do based on the arguments, prints something out, and then it quits. That's slow. It's not as slow as it used to be. It used to take about 2 seconds. Now, I think the JVM will start up in about 0.3 seconds, which is a lot better. But it's still sluggish if you are running it many times. What I want is instantaneous startup. And we're going to achieve that by running the application the first time, but not quitting when it finishes. We just keep it running in the background. And then the subsequent times we call that application, we don't start the JVM again. We just open a socket, send the parameters in, and get the response back. And that can happen in a tiny fraction of a second rather than 0.3 or 0.4 seconds. So a small change here, and I will show you what happens over here. Let's run the same command. So bear in mind that SBT is running here. It's continuously rebuilding this jar file. So this is not the same tube.jar. This time, we get an error message. It's sort of an error message. It says this application must be invoked with the ethereal launch script. Now, I haven't told you about ethereal. Ethereal is the small module that helps build daemon applications. But it tells us how we can run that. We can run Java passing this parameter, build executable. Now I'm going to call this tube. And it's told us what to do. All I had to do was specify that we're going to call it tube. So that ran quite quickly. Now that really was launching the JVM and then quitting it. But in this directory, here we have a new file. This it was here before, but it's overwritten the old version called tube. And I can run that by typing /tube. But I'm just going to prefix that with time so we can see how long it takes to start up. Okay, that took 0.7 seconds. Actually pretty slow. If I run it again, it's 0.05 seconds. Because the first time it ran, it stays running in memory. Now people often talk about Scala native being the solution to fast startup in Scala. For many applications, it can provide that. But if you have an application which has to set up all sorts of internal state before it can process requests, Scala native would have to do that every single time it starts up and quits. So you still don't get that for free. Whereas with a daemon, you can set up that state the first time it's invoked, and then subsequent calls can reuse that data that is in memory. So that is an advantage the JVM has over Scala native. I mean, you could, of course, run Scala native as a daemon. That is a possibility. But what we've got is we've made it possible to run Scala as fast as, well, probably faster than Python, as fast as Perl or Bash, apart from the first invocation. We're not gonna fix that. The other thing this newer version does is it prints out the arguments, and don't worry too much about the way they're printed, but these are not just strings. These are objects of the type argument, which have a little bit of additional information. If I run tube foo bar, we can see that foo is there in position 0 and bar is there in position 1. So argument is just a little wrapper around string, but it has some important information which will become useful a little bit later. Next stop, tab completions. So how many people use Git from the command line? Almost everybody. How many of you would be unhappy if Git did not have tab completions? How many of you would be happy? Yeah. Okay, brave people. If you're using a command line application, whether it's Git or something else, tab completions can make the interaction so much faster, so much more discoverable, and more intuitive generally. And with Java and Scala normally, if you have a 0.7-second startup, it could be very frustrating to have to invoke the application to get tab completions each time. I've actually sort of hinted at my solution here, because you could just define a tab completions file that does it, that works out what the tab completions are automatically. The approach I'm going to take, rather than define that tab completions file, which has a big problem that it can get out of sync with the actual code, I'm going to generate the tab completions dynamically from the code by running the application. And I will show you how this works right now. But I will have to jump forward to commit 32. So a few more imports here. There are some subcommands here. We're going to run this as a command line tool which takes a subcommand. We're going to pattern match on the arguments. Remember, the arguments is a list of argument types. And we're going to compare those argument types to these subcommands. If it's about, then we do this. If it's install, then we do this. If it's trip, then we do this. Now, one thing to be aware of, which I won't explain quite yet, is that I've put the right-hand side of these patterns inside an execute block. Whereas there's code here, or potentially there's code here that would run that is not inside the execute block. But before I do that, let me show you how this works. So that has successfully recompiled. Let's go back to the terminal. And in one of those commits, I think I created a make file, which will go through the process of killing the previous tube version I had running, removing the file, generating the executable called tube from tube.jar, and then I will copy it to my path. So I'm going to run this make file. So remember, SBT is building the jar. Make, which I will run explicitly every time, is cleaning the old version, putting the new version on my path. And then I can run tube type about here, and it says about this software, which comes from here. If I type something it doesn't recognize, it says unrecognized command. And if I type tube install, let's just check what that says. Tab completions.install. So if we run install, or if it matches the word install, which comes from here, then we're going to install the tab completions and communicate. That means generate messages explaining what happened in this particular case, and print out what is communicated from the installation. So let's see what happens. So it did something. Now, it did three things. It tried to install a ZSH completion script, tried to install a bash completion script, and tried to install a fish completion script. And in all cases, there was already one present because I've done this several times already. The script already exists. I could go and delete those files, run it again, and it would reinstall them. But this is not the first time. They are already there, which means that I can type tube and press tab, and it immediately comes up with these three options, along with descriptions, which are defined here. including with ANSI markup. So this is underlined as specified here by the underline here. This is in ZSH, by the way. I normally use ZSH, but if you want to use fish, then we have the same thing here. And does anyone still use bash? Nobody. But it works anyway, but you have to press tab twice. And you don't get descriptions in bash. So we've installed 3 different tab completions automatically, and in all cases, they're generated dynamically. Now, it's the dynamic generation that is the reason why execute exists. Now, I mentioned already that when you press tab, we are going to invoke the application in order to generate those tab completions. Now, obviously, when you hit enter and you run the command, you're going to invoke the application. So there's 2 modes in which the application can be started. Distinguishing between those 2 modes is a problem for the completion scripts and for this CLI block here. Now, in the case where you are hitting enter and running the command, it will find its way through to the right execute block, and then it will execute whatever is inside the execute block, sort of as you would hope for. When you press tab, it will do the same thing, but it will stop as soon as it hits an execute block. And instead of doing anything potentially side effecting or any kind of action, it will return to the tab completion script a list of completions. And it turns out that as a side effect of trying to pattern match against a subcommand about, for example, when we compare an argument, which I don't know if you remember, the argument knows its own position. It was encoded in the object. As a side effect of just doing that comparison, we can register the fact that that argument could possibly be about. We're interested in whether it's about or not. We register the fact that if and only if this fails to match, we register the fact that it might be install, and we register the fact that it might be trip. So as a side effect of just doing these comparisons, we can actually register completions kind of behind the scenes automatically, but it makes it very easy to write applications which are guaranteed to be consistent between the code and the tab completions you get. And this is important because I don't know if you've noticed, particularly with newer command line tools, often the tab completions are wrong. They suggest something which doesn't exist. And the reason is because there is a developer who cares about the tool, who implements the features, and then there's somebody who's probably 2 months, maybe 6 months behind, who cares about tab completions for their shell. And they will go and update the script for ZSH. And then somebody else will update it for bash and somebody else for fish, if you even have those scripts. So they get out of sync, and you have 4 people managing 4 sources of possible truth. Whereas here we have a single source of truth, which is the preferred source of truth, the application code itself. So this, I think, is quite cool. It works remarkably well. I could match on subsequent subcommands deeper in the arguments. And as you'll see later, we can match on parameters as well, and we can suggest possible completions for those parameters. And all of this is possible because we can run it in a fraction of a second. So we're building an application for integrating or accessing data that is available on the London Underground. And there is an API for Transport for London, which provides all kinds of interesting things. It's separated into these different categories, and you can, well, you should, if it's, there There we are. You can browse what is available. Now, if you try and find information on the stations, which is going to be our first the first set of data we're going to try and access, you will find that it recommends downloading a zip file, extracting a CSV file from that zip file, and then reading stations and station codes from that. So that is what we're going to have to do. So I think I need to be at commit 50. Okay, so what we have here, not much has changed. A few more imports. But down here, I've created this object called data, which has a method stations, which is going to return, well, at the moment, it returns something called DSV, or something of type DSV. Does anyone know what DSV is? Does anyone know what CSV is? Right. So DSV is delimiter separated values, which is just a generalization of CSV, which includes tab separated values and I suppose SSV for semicolon separated values or anything else you want. And up here, we specify the kind of DSV we're going to be working with, which is CSV with a header row, which is a significant point. The way I'm going to get this is to specify the URL. That is an interpolated string prefixed with URL. This is type checked, or it is content checked. The return type, if I hover over this, is a URL, and in quotes, there is a singleton string type, HTTPS. It knows not only that it's a URL, but that it's an HTTPS URL. If we did an FTP URL, there would be different capabilities available on that, potentially. So we have a URL, and in here is a very good example of direct style Scala. Because just here, I am going to run an HTTP GET on the source URL. That returns an HTTP response. Technically, it returns an HTTP response logs HTTP event. This entire 3-word expression is a type. It is a single type. It's written in this very expressive form. What this is telling me is that basically we're returning an HTTP response, but additionally there is logging information available in the form of HTTP event objects. We're not going to do any logging today, so I will leave that as it is, but you'll see a few more examples where we have a type that is several words using an infix type here, like logs, or later we'll see raises for errors and tracks. We will see a few examples of this. The primary part of the type is the bit on the left, and then there's additional things available through this part of the type here. This is only possible in Scala 3. So we get that, and then we are going to create a zip stream from that because we know that has content that is a zip file. From that, we are going to extract something called stations.csv. I happen to know the name of the file within the zip that we want. And that is going to be readable with dsv.parse, because we know that is CSV. We're going to try and read it as DSV. Now, you might be thinking, all of this should be in a for comprehension, and each of these should return some sort of monadic wrapper, like try or option or Zio. In direct style Scala, you don't do that. You simply return the type that you would naively expect to get if you were using Python. Well, obviously not Python, you don't have types at all, but if you were using, let's say, Java, or if you were writing a prototype. And at the moment, this is kind of a prototype. We're not doing any special error handling. And I don't know if maybe here, yeah.
I have a question.
Of course.
Does the source URL get raises anything?
Get does not actually raise anything. Because it can return a response that is a representation of the failure. So the possible failure of connection is encoded in HTTP response. But it's a question that somebody else asked last week. And I wonder if maybe it should raise potentially a connection exception, which is not the same as like a 404 error or a 500 error. The 404 error or 500 error comes when you try to stream it. And what is completely invisible here is, and this is an important feature, source_url.get is an HTTP response. We can read that. We can stream that as what is the most fundamental streaming type in Scala, which is a lazy list of arrays of bytes. In particular, in Scala 3, we're using immutable arrays, so you can't accidentally modify the contents. So this is a lazy list of bytes, and that anything that can be interpreted as a lazy list of bytes can be passed as a parameter to zipstream. So I could put a file in here instead. I could put a string. You can read a string as bytes. You could put a byte array. All of these things are possible parameters here, and by virtue of some type classes, which you don't even need to see, it becomes possible to read things. And likewise, dsv.parse can read anything that is streamable. When we extract this one file from the zip file, that result, and extract produces a zip entry. Zip entries are readable. You can read a zip entry as a lazy list of bytes. But we don't have to write all the code to marshal it into the right types. This happens automatically because there is a unique solution to wanting to read these things. And it's able to work it out through implicit search. Now, all of this compiles. And I think if I run this, there's probably nothing more you can see because I don't actually... I know there is something you can see. So let's try and run this. But one thing to note before we do, because as I've said, there is no error handling. So we are permitted to write this code only because of this import here. Import strategies.throw unsafely. This is saying, I am coding in prototype mode. If there are exceptions, don't check them. We're not going to check them. We're going to let them be thrown and deal with the consequences. And soon I'm going to remove that, and it's going to introduce all sorts of compile errors because we must then handle those errors. We're not allowed to write code that can potentially fail. Let's just make that. And that is running. If I run tube trip, it's going to connect to the internet. That was actually pretty fast. And it has printed a table. Now, this is going to be more apparent if I shrink the font size a bit. Quite a lot, in fact. Okay, here is a table of all the data it got from that CSV file, rendered into a beautifully aligned ASCII art table. And I don't know if you can see, I'd be surprised if anyone could, but these, in this column, are lists of stations. On the left-hand side are the codes that are used to represent those stations. So we will use these codes in later API calls. That's why I need this information. I can't make the API calls without that. And yeah.
So can you return to the table? So you have faults in the camel case and true in the caps lock. It seems like a bug in the...
No, because these are just strings.
Is it what they return?
It is a bug in, well, it's arguably a bug. It is
transportation system.
Yeah. They expect you to deal with that. And do you know what? I imagine that this is an export from an Excel spreadsheet. And when they build a new station, and these last 4 stations at the bottom are the 4 that have been added in the last 10 years, I think. They have slightly different codes. I think they just add entries at the bottom. And some people type the entries in all caps, and some people type them with the capital letters, some with the lowercase, and they just export it. So that is why we have a mixture. Now, thankfully, we only need the first two columns. So all of these additional columns we're going to ignore. I just want to show you back here. That table exists because I called dot table on the result of stations. Stations is DSV. And we can call dot table on anything that can be presented as a table. And that usually means sequences of things which are convertible into rows. And DSV is certainly of that form, but also you would have other things like a sequence of lists or a sequence of arrays or tuples that could be viewed in that form as well, and even a sequence of case classes. So yeah, this is uninterpreted data, which is why it's a bit of a mess. So let's try and interpret the data. Commit 58. Well, there's one other thing that I forgot to mention before. This get call here, this HTTP get, here's the definition. It requires a contextual instance, an implicit instance of something called online. And I've actually said stations use this online. Now, all of the HTTP methods defined in Soundness require this thing called online. It doesn't do anything. It is just a marker implicit. But it only allows you to call an HTTP method or make a request in a context where there is this online. Now, what this means is that you can be very careful about which methods in your entire code base are able to do online stuff by granting them permission through this implicit. The implicit is actually erased, so there is zero runtime cost to this. It's not even an additional parameter. It gets completely erased, so it exists only at compile time. But the constraint is the same. So there's a little bit extra here. We're now getting the rows from the DSV, and we're mapping across that into station row, which is a case class I've defined here. And this is doing generic derivation on a very small scale because we've got one case class with two parameters. But it's trying to extract elements of different types, the name as text, and the identity as this name type here. Now, name is a general type for identifiers. And that's provided in a module called nomenclature, which appears to be triple underlined here. I don't know why. By the way, it's called NAPTAN. This is just the name of the identifier in London Underground terminology. They call them NAPTAN codes. So that's called NAPTAN. And this definition here, again, it's erased, is specifying the valid identifiers for a NAPTAN code. Now, when we try and parse some string data from CSV as a NAPTAN code, by virtue of this type here, now this is just one type. NAPTAN is nominative under must match and then a regular expression. There's no value in existence here. This does not exist on the heap. This is just one type which encodes in the type the constraints. We are under those constraints that those identifiers must correspond to. And when we try and decode that, which happens automatically when we do generic derivation, it will check those rules. And there's different rules you can put here. You can say it must start, must end, must not contain. And we can actually have yeah, Nick.
And what if this rule doesn't hold?
Yeah, so if the rule
Phrase?
is it
do you have some sort of runtime error, or what happens if the rule doesn't hold?
So an exception is thrown.
Okay.
Now that's usually bad, and
it's because of the throw unsaved, right?
We are allowed to compile this because this does compile. We're permitted to compile this because throw unsafely is here. Now this rule is actually wrong. Here's a different rule which is wrong. So we can change it from one to another. This compiles, but if I remove that throw unsafely, we will see what happens. Okay, so 3 errors found. It's actually not very many, but by virtue of removing that prototype mode, throw unsafely, we must now deal with checked exceptions. And I'm going to do this step by step. So we have errors here. Don't worry too much about what the errors are. The most interesting thing is that we get errors. We are stopped from compiling. And a lot of what I have put into these libraries is to try as hard as possible to make it harder for you to write code that shouldn't work, to get to move errors from runtime to compile time. That is my goal with so much of the code I put into these libraries. So here we have something which is stopping you putting this code into production. Now, quick way we can fix this, because if installation of tab completions fails, then there's all sorts of things that can go wrong. Can't write to the file, can't find a directory to put it in, and so on. We're going to wrap that in safely, which is think of it like a try and catch that does nothing with the catch case and just returns, as if it returns an option. For this case, it just avoids the problems. If there's an error, we silently ignore it. Now down here, we have a bigger problem. And the reason we have problems here is that there's so many things in this expression, single expression here, so many things that can possibly go wrong. We're doing an HTTP request, so we might get a failure with HTTP. The zip file might be corrupt. It might not be valid CSV. All of these are possible failures. And since we are using generic derivation to try and extract these as station rows, and the extractor that is derived generically for things typed name naptan can potentially raise a name error. If it's not, this is the answer to your question. It's a possible name error, but we're forced to handle it. So we can do that by wrapping this in something that is basically equivalent to a try catch. It's a little bit more clever, but the first thing you will notice is that the try and the catch are reversed, and the catch is called mend, meaning to fix, and we have a within block underneath it. So that previous expression appears inside within, and we're going to mend any kind of HTTP error by just silently returning an empty lazy list. This is our first attempt at a solution. We will do the same for zip errors. Now you'll see that we have different errors here, and the errors are moving as I deal with more cases. So name errors we've handled, and we have one more case to fix, which is DSV errors. So we're forced. The compiler is telling us, you must handle all of these cases one way or another. And this is in many ways equivalent to what you would have to deal with if you were writing a for comprehension with monads that operate on different values. Except we can compose this as a single expression in a way that would not be possible in a monadic with a monadic approach. So this now compiles. But I'd actually like to use a variation on mend, which is called tend. And what tend does is it takes one error type and sort of converts it to another error type. So I've just introduced something called init error. This is an initialization error. This code to get the stations happens when we're initializing, so it's an init error. And the definition is just a subtype of exception, which comes from error here. And we need to return an exception type on the right-hand side here. So I'm just going to go and replace these with init errors. I don't know if you can see through the red squiggly lines, but the right-hand side is a different error. This is going to be a user-facing error for every kind of possible thing that could go wrong here, telling the user how to deal with it, how to fix it, and maybe even some advice. Why are there red squiggly lines? Well, there's now a new kind of unchecked exception, or sorry, it's a checked exception, that's the problem, but we haven't handled it, called init error. And we need to fix that by declaring in our method return type that we raise init error. So when you call stations, in the same way that you would write throws in Java, you're forced to handle those exceptions. And up here, there is a new error because we're not handling init error in the body here. So a few more changes. And in this body here, if we get an init error, then it's kind of game over. If we can't initialize the application, we can't do anything with it, we might as well quit. So we shut down everything and we return exit status 2. Let's say exit status 2 is a serious failure. Exit status 1 is just user input is bad. So that is a very brief view of the start of error handling using Soundness. And all of the different libraries in Soundness take advantage of this and give you composable expressions which have composable errors. I did that, made it safe. I'm just going to jump forward a little bit and tell you what I've done next. I'm not going to talk about the code. So I'm going to go all the way forward to commit 102. And what that will do, we have added several more cases here, which are all being processed here. But what we don't want to do is every single request, download the zip file, parse the CSV, get the codes out just so we can send one request. We want to save that file locally. So there's some additional code here which caches the download. Nothing more than that, but it has to be done safely. It needs various implicits relating to the file system. You need to know whether we're dereferencing symlinks when we access. All of this has to be specified. Nothing is presumed. And the reason nothing is presumed is because we want to force users to think about the decisions that can avoid possible bad assumptions later. So our application, as it currently stands, doesn't do very much. It runs the code to get the list of stations, but doesn't print anything out anymore. So I won't try and run it again. We will now go on to parameter completions. So the way I want to use this, I want to search for a trip from start location to a destination. So commit 119, and this is probably about halfway through the entire code, halfway through the development process. And up here, I've added start and destination. And down here, inside trip, this is where the significance of these execute blocks becomes more important. Because inside execute is where we're doing the actual work. We're going to print out that we are searching for a journey from the start to the destination. We're also potentially going to throw errors if we have an invalid start or destination specified by the user. But before we get to execute, we're going to do the work that would be done whether we're doing tab completions or whether we're doing normal execution, which includes selecting the start value as a parameter from the list of stations. So the stations are generated first. then we select one of those values. And there's various type classes involved here that make it possible to just pass these values, pass these types into the method select. But from the start and the destination, we're going to select a station. And how that looks, let's just check that compiled. Yeah, success. So let's make this a bit bigger for you. So we'll make that. So tube trip, there was a little delay, so I knew it restarted again. If I press tab, first thing we get is a dash. If I press tab again, we have two suggestions for completions for the parameter. Let's do start. That completed, press tab again. Do you want to see 506 possibilities? I said there are over 200 underground stations on the map. There's actually 506 possible destinations, which includes things like tram and other kinds of railway line. So this list is generated dynamically by the application when I press tab. Basically invokes the application, generates the list, returns it in the appropriate format, and lets us choose. So this is where you have an opportunity to tell me your favorite London tube station if you visited. Anyone? Piccadilly. Pick tab. Piccadilly Circus. Anyone else? Waterloo. Searching for a journey from Piccadilly Circus to Waterloo. So I specified these in a. I converted these in the code to a kebab case because it's easier to type. And as you will see in the code here, at this point we get from the optional one. So when we're pressing tab, we might not have a finished command line. We might be work in progress. We've only specified the start, for example. And actually, one clever little thing I can show you. 506 possibilities when I press tab on start. 505 possibilities for the destination. And that's because when I'm generating the list for the destination, sorry, not here, just up here, I remove whatever we chose for the start because you don't want to go from one place to the same place. It's not worth taking the tube. That's why the number changes. So we have a functional dependency between the parameters, and you can do a lot of things with that. Now I wanted to show that here, start, we're not working at any point with strings, or it's called text. There's a more type-safe string called text in Soundness. We're working with a case class that is a much better representation of that value. Nowhere do we even do any obvious string processing. It all happens behind the scenes. Now, I gave this talk to the Dallas group in Texas remotely about a week ago. And I had to wake up at, well, I didn't wake up, I stayed up until 1:30 a.m. in order to give the presentation, which is midnight in London. And I didn't actually start speaking until, I think, 1 a.m. in London. You'll see why I'm telling you this. And by the time I got to the point where we're actually sending requests, it was probably closer to 1:45, at which point there are no tube trains running, which meant that I discovered I worked out on the day I was giving this, that we would get no results and there would be no interesting results coming back because all of the tubes are closed and it would only present walking results. So I added a new parameter called departure, which allows you to specify the departure time. Now, the format for that, this is part of the API. It's just I didn't imagine it originally to be part of this application. the departure time, we're going to match down here. Now, departure is an optional text. So if they provide it, we get a text value. If they don't provide it, we get something called unset, which is equivalent to none. Now, here, this is inside the execute block. We're going to pattern match on that with an R interpolator. R is for regex, a regular expression. Now, my first attempt is to match on 4 characters, ... That will match any 4 characters. What we want is 4 numbers. So we can write inline a regular expression. Now, if you think about it, 0000, so midnight, until 23:59 means that the first character can be 0, 1, or 2. Second character can be 0 to 9. Then the minutes can start with 0 to 5, and the last character was 0 to 9. So this is closer to what we want, but we're not quite there yet because you could type 26, and there's no 26th hour. So let's extract from that HH, this is the hour, the 2 characters that are the hour, and you can write this inline in the pattern extractor, and this will extract into a string called HH. HH would be available on the right-hand side if I chose to use it, which would be a 2-character text string. Now, we want to check whether that string represents a number between 0 and 23 inclusive. But we want to convert it to an integer first. So we want to pattern match within the extractor. Now, I know this is an extractor inside a regular expression, but we're going one further. And that extractor is going to use something called the as extractor, which is parameterized. Now, this is a new feature of Scala 3. You can put a type parameter on an extractor, which can pull in an appropriate implicit corresponding to converting to int for use in that extractor. Now, this will match if this happens to be an integer. We happen to know it's already an integer, so it's guaranteed to match because it must be 0, well, it must be 2 digits. But now, HH is typed as int, and we want to check it's within a certain range. So over here, I will add a range check. This is a very normal looking guard clause. Is everybody okay with that? How many people here have maths or science education of some sort? Does anything concern you about the way this is written in code? Would you prefer it to be written in a different way?
Well, I personally never saw when you say 0 is less than variable. I would have never written it, but I'm sure if it's better.
Okay, so I will tell you where I'm going with this because you might wonder why I'm even asking this question. We can write 0 less than HH less than 24. This is how you would write it in mathematical notation or scientific notation. You would write a single range expression. And this just uses a quite cunning macro to work out whether it makes sense as the intersection and of 2 conjunction, should I say, of 2 inequalities. So if you write it like this, the macro kicks in and realizes that there's a better way of, well, there's a more computer science type way of writing this. But as programmers, we get to see it in the form that at least I would prefer to see. So we get the timeout, and we will use that in the requests later. We saw pattern matching. Let's go on to generic derivation. We saw a little bit of that before, but now is the time to maybe explore it a bit more deeply. How many people have encountered in some form generic derivation in Scala? how many people know what I'm talking about when I say generic derivation? Nobody's confident. That's fine. I don't mind if you're confident about it or not. How many people don't know what I'm talking about at all? Now, there's a big gap in the middle of people who haven't put their hand up. I think nobody's confident to say they know generic derivation. I don't know if you're embarrassed to say you don't. You shouldn't be. And then there's people in the middle who don't want to admit to anything to do with generic derivation at all. So generic derivation is a means for us to generalize extractors or type classes of some sort. They can be extracting from JSON or serializing to JSON. This is a very common example. For compound types that are composed from other types. In Scala, that usually means case classes. So if you imagine we have a case class that has case class values within it, which themselves have case class values, and we have a sort of deeply nested structure of case classes, ADTs, that represents the structure of our data. Maybe there are lists of some of them, and maybe some of them are optional. And at the end of all of these, there will be some primitives. There will be probably integers, there will be text values, there'll maybe be doubles. So there's lots of composition of case classes, but ultimately it's a composition of like very primitive basic types, Booleans, strings, numbers, and so on. Now, what generic derivation says is if you can extract strings, let's do the JSON example. If we can extract strings from JSON, if we have a way of extracting integers from JSON, if we have a way of extracting Booleans from JSON, then any composition of case classes which relies only on those types, or on any types that we know how to extract, we can compose automatically without writing any boilerplate. We can compose an automatic way of doing the extraction of the entire data type. Now, this is relevant for this particular example because here is the JSON result. It's in Firefox because it presents JSON a bit more readably. We have an object here which has journeys, and there's an array of results from the journey. There's a start time. This is just a string. There are several legs to the journey. I don't know if you know this word legs, used to mean steps in the journey. You take one leg, you change to a different train, you take another leg. And then each leg has various things. There's a path. The path has a string representing the geographical coordinates of every point along the line. I mean, there's lots and lots of data that we get back when we call this API. And we want to convert this automatically using generic derivation into a single instance of a case class which refers to other case classes. So we will do that by, is it done already? Not yet. Because I need to go to number 164. So let's jump ahead. So 164. So down here, there's a whole series of case classes which refer to each other. So journey contains a list of legs. Leg contains, for example, instruction. Instruction contains text. So there's primitive types like text. There are references to other case classes. And overall, the result of this query is going to be an instance of plan. And we will do that by just typing as plan. That's it. It's done. We have taken this result. This I didn't actually show you this being done, but this is sending an HTTP request. it is parsing it as JSON. When we parse it as JSON, we get a dynamic JSON object. We don't know anything about the contents of that. And then we have to convert that JSON into a typed case class structure. Again, it's a single expression in direct style Scala. We convert the whole thing to a plan. And it works, it compiles. There's no but, this works. Let's try and run this and see what happens. Oh, by the way, we do need to handle HTTP errors. We handle JSON parse errors. These are the ones from just parsing the text as JSON. And then JSON error is, for example, if there are missing keys in objects. So these are handled and they're converted into user errors. So let's try to make this again and run it. Okay, we got an error. Unexpected JSON response. The JSON value had type number instead of array when accessing this URL. So that's the request we sent, and we got unexpected data back. It's not that helpful. I mean, there's some useful information there. It tells us the URL because I included the URL in the error message here. But we don't know where in the JSON this happened. We know that it was a JSON error because that error message matches JSON, but we don't know which object had the problem. We don't know which element of which arrays. We don't know the path to the problem. Now, this is one of the coolest parts of Soundness, but it's quite nuanced in how it works and why it is useful. And I'm going to show you a couple of slides. This is what happens when we try to call as. This is the method that extracts a value of a certain type that we specify from some JSON. The compiler requires an implicit tactic. Tactic is the type class type that handles errors. We need a tactic for handling errors. So this is the means by which we check exceptions. You can only run a method which raises a JSON error if you have a tactic in scope that is able to handle it. So we need that. We call it with implicit search, or it gets called by implicit search. Now, when we have generic derivation, that is going to look for different types that all come from plan. So if we try and get the type int is decodable in JSON, this is a very expressive type. This is just one type. It's 5 words, but int is decodable in JSON. Text is decodable in JSON. Tube line is decodable in JSON. Location and timestamp. These are all types that exist in our case class structure. And as I said before, generic derivation allows us to compose decodable type classes if they exist for the primitive types. The primitive types are int, text, tube line, location, and timestamp. So what that means is implicit search will go and try to access these decodables. Now, most of these exist already. There is a decoder for tube line, the timestamp, location. I've provided all of these. But it could return invalid data. What if it returns a tube line that's not a tube line we know? Tube line, by the way, is a Scala enum. Location is geographical coordinates. We expect them to be an array of 2 floating point numbers, but what if it's not? Timestamp is a string that's in a particular ISO or RFC format. What if it's not? Well, those decoders themselves are defined to only work in situations where there are tactics available for handling them. So we can only decode a timestamp if we have a tactic for handling timestamp errors. We can only decode a location if we can deal with location errors. what that means is that when you call .as on a complex type, you might be demanding all kinds of handling requirements that the compiler is going to enforce. The compiler will not let that code compile unless it knows how it's handling all the possible errors that might occur. So when we run this, if you imagine that complex JSON structure, there might be locations dotted through the code, there might be timestamps dotted through the code, through the JSON code in different places. We need to know where those are in order to investigate what's going wrong. And I can tell you that timestamp error is defined in a library that has no knowledge of JSON. It doesn't have any capacity to hold a reference to JSON. Location error doesn't have any way of referring to the path in the JSON where the problem occurred. They're two orthogonal things. The location where the error happens and the composed type, or just the type of the exception, are defined in different places and are completely orthogonal. They have no knowledge of each other. But what we want to do when we handle the errors is bring those two together. We want to know what error happened and independently or orthogonally where it happened, so we can present a message to the user that deals with that. And if I look at the definition of as by hovering over it, just here, you'll see value type. Well, if we do as value type, it returns a value type. Direct style Scala returns just the raw type, but it raises JSON error. In all cases, you can get a JSON error. And it tracks JSON path. Tracks is an indicator in the signature of the method that we have additional information available to us that we can use in the error if we choose to. And we do that by changing tend to track. Let me just jump one further. We're going to track JSON paths in this handler here. And the first thing we're going to do, I think this is the point I want to talk about. Here is a user error which is empty. And if you look at the definition of user error here, it's my own error. It can have any number of messages. It can aggregate multiple errors. So you can create a user error which says 10 different things are wrong. That is a feature of this particular type. We're going to start with a user error that has no messages. It's empty. And then every time an error occurs, like an HTTP error, a JSON parse error, JSON error, we're going to take the existing errors, or the existing error value we've got, which is called accrual. And Nick has told me that as a non-native English speaker, accrual is a horrible word to work with. So I might change that. Accrual is a common word in accounting, financial accounting. You talk about the accrual of money or wealth. Here, it means the aggregation. And we're going to add a message to that. And this add method is defined in user error. So this is very much like a fold left. We start with an initial value, like an empty list. And every time we get an error, we're going to fold it into the value. And if you look just here, focus is going to be an instance of this type here, JSON path, which tells us where the error occurred. And we are able to do that because we track it. So when we call as, it navigates through the hierarchy of case classes. It knows where it is when the error occurs, whether it's a JSON error, a timestamp error, a location error, or some other error. And that focus is attached to that error message or to that exception. And when you come to handle it, you have both available in the same place. You have focus and you have the error type, plus any parameters that we can extract here. So if I compile this version here, well, it's already compiled. If I make it and try and run that again, I think we've actually only got there's only a single error, but it has told us now that it's happening at the journeys key here. Now, I don't know if I can find a more problematic. Okay, this one was successful. This is successful, and it shows you the results that we got. I didn't want to that. I wanted to find something that was, I think Woolwich Arsenal is a problematic station. Problematic, but it's only got one problem. You'll have to trust me. Sometimes you get multiple errors coming back. And in that case, you would get multiple error messages, and each one would have a different location, and you could probably infer from that what is going wrong. What you would probably do is take this query URL, put it into the browser, and just look at the response you get back. And I know there's certain issues that we're not handling here, and we would need to handle those in some way. Okay, I am going to push forward because I'm 2/3 of the way through, and I'm probably more than 100% of my time. But we talked about multiple errors. We did that. Showing the route, you actually saw that by accident because it comes back with a response here. This is option 1, takes 40 minutes, and we're getting this information here. It's got a list of the stops along the way. This is formatted results for running the query. And in here, if I show you the trip, we match on the trip. This code here, it says we're searching for a journey, and then for each journey in the plan, we print some stuff out. For each leg in the journey, we print some more stuff out. This is how it is going about printing it. We are just diving into that data and printing it out in a quite simplistic format. We can do better than a simplistic text-based format. We can do ASCII art. So I'm not going to show you the code so much as the results. Let's jump through to 191. Hopefully SBT is, I think has compiled that. Let's go back to the terminal. We'll run make. And that one, I think, worked. Piccadilly Circus to Galleon's Reach. Well, option 1, it draws a little tube line in ASCII art. Tottenham Court Road, Farringdon, Liverpool Street, Whitechapel, and so on. I happen to know that you need to change trains at some point along here, and it hasn't shown this in any particular way. So we can go a bit further, and let's display. Actually, maybe my slides tell me where to go next. 198. We're going beyond ASCII art. We're going to Unicode art. So let's see 198. And that has nearly compiled. You might have noticed that compilation has got slower. 7 seconds for about 200 lines of code. There's no sound yet, but it's coming later. I just remembered to turn it up because, well, we'll see. Let's make it. Let's run it. Come on, TFL. There we are. Okay. So we've now got something which actually looks a little bit like a tube line. And it tells you where you change. It tells you all the stops along the way. And there's a few things it doesn't tell you. It doesn't tell you how long it takes or what time you start. So we've got one change here very quickly, then another change, and three changes. This is quite a complicated route. Some of them are more straightforward. Some of them are quite long. Does anyone want to suggest any stations? I'm just going to go for the stupidest names on the tube. Tooting-Bec, I think, is one of the stupidest names. And Cockfosters. So Tooting-Bec to Cockfosters, Northern Line, then Victoria Line, then Piccadilly Line. Okay, I mean it seems to work. You probably don't know London well enough to tell me if these are the correct stations and correct interchanges, but I trust it.
Did the Dallas people knew London?
Sorry?
Did the Dallas people knew London?
I don't think I asked them actually, and because it was remote, it was a less interactive conversation. But I mean that's a kind of a cultural question. Do people in Dallas go to Europe? I don't know. Most of them actually weren't in Dallas. They were dialing in from elsewhere in the US. Let's add some color because it's a bit monochrome. So 207. And while that's compiling, I will just show you what has changed. We have an output object here, which is dealing with display stuff. I have a list of values here. Does anyone want to guess what these are? Do you recognize them? These are Unicode character entities. If you hover over that, you'll see that that is actually a character. What I could have done is written open quote and copy pasted a character that I grabbed from somewhere in a Unicode table and pasted it. But instead, I used this string interpolator, which looks up in the Unicode table the names of the characters and returns the right one. It makes the code a little bit more self-documenting, possibly. You might just think there's no point. It's an option that's available. We're printing some output here. We substitute the color value into the string. It is an E prefixed string, which makes it able to use ANSI escape codes. And then we print more stuff out. We print stuff out for each leg. We slide across pairs of stations, which makes it possible to do certain things. The implementation is not too complicated, but maybe you need to know a little bit about how it works. Let's see what it looks like. We will make it. We will run it. Same one again, Tooting-Bec to Cockfosters, and we now have, it's a little bit too wide for the page, but we've now got different colored lines. So this light blue one is the Victoria line, this black one. This is why I chose a blue background, because it means that the black shows up. And one of my favorite, one of the most interesting tube routes is if you start in a place called Ruislip, it's difficult to pronounce based on the spelling, and you go to West Ruislip. Now you might think this is going to be one station stop. This is not going to be a long route. Oh, okay. No, they didn't. There's actually a complexity in the data which I fix in some of the later commits. I will do this demo in about 10 commits time when you can see the result. Let's just give you one more example. Walthamstow Central to Piccadilly Circus, maybe that will work. No, the problem I think is Walthamstow Central. Pimlico to Piccadilly. Okay, I mean still the two blue lines. I wanted to show some. There's also a walking route here. Maybe this one. We've got a red line. Okay. So just to prove that it doesn't have only blue colors. What do we here? We've added some color. Timestamps. Now you might have noticed, I did talk about timestamps with respect to generic derivation. Not there. But this is not the most readable format for time. I mean, it's correct. It's in London time, but this is actually just a string. It's the string that we get back from the JSON. I know I talked about timestamps being parsed during generic derivation. It wasn't actually doing that at that time. I'm going to add that in now. So let's see how that works. And we need to go to 208. I think our finished number is 255, which gives you an idea to how much longer I'm going to go on. 208, here we are. Use timestamps for arrival and departure times. So what I have done in this, we've got lots of errors now, 6 errors, and these have all occurred because looking at this diff, I have changed arrival time to a timestamp and departure time to a timestamp in, where is it, line 195. So down here, these used to be text, but now they are timestamps. This is a dedicated type for time. And what errors has that created? Let's go to the start. Start of the errors. They're quite long. So the first problem is that we can't substitute a timestamp into a string. It doesn't know how to render it. So if you use the S interpolator in normal Scala, it just calls toString on a value. That is completely unacceptable in Soundness. You can only substitute a value into a string if there is a showable type class which defines the way that will be converted to a string for human readability. And in order to get them showable, we first need to introduce a time zone, because these timestamps as they are presented are in London time, whatever that happens to be. So we define a time zone, which is just here, line 28. That uses the TZ interpolator, which checks that Europe/London is a valid time zone. If it's not, then it's a compile error. So with time zone in scope, we can then specify, for example, somewhere down here, 159, we can then write in time zone. So the timestamp is actually a date and a time. We're going to turn it into a local time by specifying the time zone. And then we're going to throw away the date, because it's always just the next day, and just get the time. And time is printable, or it can be substituted into a string because there is already a showable type class available. We have one remaining error, which is a complicated one, but it is happening. It's one of the biggest ones. I just want to find the line number. I'm going to have to. It's in one of these as methods. It's not this one. It is this one here. So here, super long error. Like you have no hope with this. I'm going to hope and put the case forward that those error messages will get better with some help from the compiler, but it's not happened yet. But the problem, I happen to know what the problem is, which is that plan has changed because it now needs the ability to handle timestamp errors. We change the type from text to timestamp. We've got new possible errors that can occur, which means we need to introduce in our track block handling for those errors. So we'll just add that. We'll add timestamp error, and then suddenly everything compiles. Not suddenly, it's quite slow now, but it does at least compile. And if I make that again, do the same trip, we will see that we now have a more sensible rendering of the time. Okay, nearly there. The route, I don't know if you remember when I looked at the JSON, we had lots of coordinates. And for some reason, I'm not really sure what that reason is, the way they're passed into the JSON is in a string. So the string contains JSON, but for some reason, they serialize that array of, it's an array of arrays of doubles. They serialize that to JSON and put that in a string inside the JSON. What that means is that we have to handle that. We can create a type that is called root that represents that, and we can write our own extractor that deals with that particular format that TfL have used for their data. That's fine. 235. Let's jump forward. I'm not going to show you how that works, but basically I read the JSON, I extract it as a string, and then I convert the string to JSON again. So I parse the JSON twice and then do the conversion. But I will show you the line that occurs at, because it is line 34. So remember, it's in the JSON as a string, and then line 34 defines a given. Now, this given is maybe interesting. Let me just show you the full size there. This is a given definition. It's like an implicit value. And if you read it from line 31, it says given using tactic JSON parse error and tactic JSON error goes to root is decodable in JSON. Now, given definitions like this will right now probably look very complicated, but you can become very familiar with them and what they mean. What this is saying is we're generating a decodable instance that makes it possible to decode a root. Therefore, a root is decodable in JSON. But in order to provide that, we need in our context a tactic for handling JSON parse errors, because we're parsing that string a second time, and a tactic for handling JSON errors, because it might not be an array of arrays. Either of these things could go wrong. So this is a decodable, but the decodable instance is only valid in a context where we have a tactic for these two error types. And we have a tactic for handling those error types if we are using this decodable in a context that can already handle them. For example, attend block, amend block, or a track block. Any of these blocks provides the context. It generates those tactic instances for handling those different error types that are listed in the definition. So the first step I have taken is to define how we are constructing a root. Now let me show you the definition of root, which is somewhere here. It has the points, which are a list of locations. Location is a type provided by shapeless. It's not shapeless. Soundness. No shapeless here. Yeah. Provided by Soundness, which gives you a definition for coordinates on the surface of the Earth. So two doubles, basically. And this is just a list of them. Now, how would we calculate the length of those? So there's a couple of questions here. We've got a sequence of locations in order, we can calculate the length by adding together the segments from adjacent pairs. So we can do a slide over them pair by pair and add up from A to B. There's also another question as to how you calculate the distance between two coordinates. And the answer is on Wikipedia or ChatGPT if you prefer. There is a formula called the Haversine formula or Haversine formula, which calculates the distance as an angle in radians between any 2 points. I mean, for these points, they're going to be quite close together in the entire sphere of the Earth. And we can multiply that by the radius of the Earth to get an actual distance. So let's do that. We are calculating def length. So we've got the points, we are sliding over them, we are summing them by, for each, this should actually be points because it's a pair of points. Is that right? Well, yeah, this point is actually referring to a pair of points. There's 0 and there's 0.1. But we are going to calculate the surface distance between them, line 223. We are going to multiply that by 6,371 kilometers. And this is actually a type with, or this is a value, a quantity with units. So if you multiply a pure number, 6,371, by 1 kilometer, you could use meter and multiply this number by 1,000, but we're going to use meter wrapped in kilo. You can also put giga or tera if you want really big different distances. We're going to multiply that by the surface distance, which is the number of radians. And what we will get back is an instance of quantity, which is parameterized on the type meters. So this is a number that's not just a pure number, it is a number with a unit. And we can combine these with normal arithmetic. This is actually a feature that is in, I think, F#. You can have not just numbers or not just floating point numbers, but you can give them all units. And if we go a bit further and calculate distance, we've done that. Print the distance, specify a way of printing it. Now, calculating the speed is what I want to show you now. Because having done that, let me just check the line number, 205. The distance is the sum of the legs. So each leg has a sequence of points. We add those 2 or 3 legs together, and we convert those to miles because this is in Britain and we have stupid units. And the speed is going to be the distance divided by the duration of the journey. So we know from the data how long the journey is. And that will work out the quantity we get from that. I should show you also the quantity from duration is a quantity of seconds. And it says seconds 1 because this is seconds to the power of 1. We would just call it seconds. But if we had an area, that would be meters with a 2, meaning meters squared. We don't have any powers of 2 or more, but if we divide distance in miles to the 1 by seconds to the 1, is it seconds? It's the wrong units anyway. We get a result in miles per second. Some very small numbers. Mile is very big, a second is very quick. You don't travel many miles per second. So what we will do is specify that we should convert that into miles and hours. Now you just say in miles. That means miles is a type of distance. The distance part will be converted to miles. Everything else will stay the same. Hours is a unit of time. The seconds, which is the time element of that, will be converted to hours. So the result we get here now is in miles to the power of 1 times hours to the -1, also known as miles per hour. This is the unit of speed that is used in Britain for historical reasons. And we will print that out. And this is a quantity which has its own showable type class available, which means we can just put it into this string and it will render in an appropriate way. Let's have a look. Make Pimlico to East Acton. 30 minutes is the duration, 3.6 miles, and the average speed. This is about 11 or 12 kilometers per hour. It's really slow. But when you have a big city and you have a lot of people moving and it's stopping every half a kilometer for 1 or 2 minutes, you don't move very fast from one side to the other. So we've calculated the average speed, and it's also printed the units in a meaningful form. There's also various checks done. So you can't add hours and miles. You can add them together because they're units of different quantities. If you wanted to add hours and seconds, that's permitted. So it would allow you to add that. You would get the whatever comes first. It would do the conversion as necessary. This makes it very difficult to make I guess you'd call it a homogeneity mistake, where you mix up your units. And I was doing an example of this library, quantitative, using, I don't know if you know Newton's laws of motion. It's like S equals ut plus a half at squared. It's like relating acceleration, velocity, start velocity, final velocity, and time, assuming constant acceleration. And I was getting this compile error. It was saying like your equation is wrong. I thought, oh, there's a bug somewhere, and I'm going to have to dig deep into this macro to work out what's going wrong. But actually, I'd actually got the equation wrong, and it had found the error in my code because I was adding, I don't know, an acceleration to a velocity. It found the error. It prevented me from putting that code into production. Okay, it's only a couple more things to show. Speed, I showed you that. Audio. Let's listen to some audio. How many people here? Sorry? No, we're not. But if you were using this command line tool and you were blind, for example, or you, I don't know, just didn't want to open your eyes and you wanted to type in the dark, you could use this. So let me move forward to, what was the number? 248? Was it 248? Okay, I trust you. Yeah, it's compiled. We will make it twice, didn't mean to do that. And let's go from Pimlico to East Acton. Sound is on. Maybe it wasn't 248, or maybe the 248 here is wrong. It's obviously is 248. Make maybe it's okay.
Something that in the presentation you just
Hello.
thought it was on 250. So the previous slide was saying 250.
I put it forward actually.
Okay.
Maybe it's from this.
I don't know because
Hello.
so it says hello.
Hello.
For some reason, this is not actually producing sound. I don't know why. But I will tell you what it's meant to do. I mean, I think most of you probably use a Mac. You've maybe seen the say command, which you can pass a string to, and it will say what's in that string. That's what I'm trying to run. And somewhere down here, I am starting a command, which is a shell command, which is to say a summary of the journey. So I construct the summary as text. I create the command just by putting it in this sh interpolator. You've seen these interpolators quite a lot. It's a theme to how I write this. And it is also checked for consistency. So if I include a long string with spaces and new lines, and I pass it in as a parameter like that, it remains as a single parameter. It doesn't just do a string substitution and hope for the best. That's a terrible idea. It makes sure that it is safely inserted into the command and it is run as a single command. I don't know why it's not running or why it's not playing, but what's meant to happen is we run this search, it finds a result and tells us what it was. Maybe a different, maybe destination Marble Arch. Nothing. Silence. That's a shame. Never mind. So almost at the end. The thank you slide is a little bit premature because first I want to show you what happens when we add a little bit more. I don't know if you remember close to the beginning, I had a command called about, tube about. I need to make it first. So this is what it used to do. Now if I run make about, we can load an image from the class path in memory and render it to the console. And this is renderable because I don't know if you can see this, each character has a background color and a foreground color. And if you set half of the block to set it to half a block, you will see the foreground color at the top and then the background color at the bottom, which means that you can print something like this out. This is all stuff that's available in Soundness if you want to use it. Not available in Shapeless.
Maybe it plays sounds now because you may actually run a make file.
Maybe. Did I forget to run make? Or...
Yes.
Take the Victoria line towards Walthamstow Central at 8:01, and Oxford Circus. Change to the Central line towards White City at 8:11. Arrive at Marble Arch at 8:13.
Good. So that is almost everything I have to show you. There's one little thing I added quite recently. And this is maybe interesting for some people and other people will possibly not care at all. The size of this executable is 14 megabytes. Yeah. So the size of this is 14 megabytes. Now, I grew up with a computer that had 32K, and to me, 14 megabytes sounds enormous for something like this. People in the audience younger than me probably think 32K is like the size of a file name or something. And 14 megabytes is nothing. And yeah. To me, it seems quite big to be distributing this is quite a small application as a 14 megabyte file. So there's some more changes. My make file I have modified a little bit to use a new tool I've written called Burdock. It's still part of Soundness, but if I just rerun, I've changed the SBT build, so I'm going to restart that, redo the assembly. which now takes, this is from cold, so it'll take quite a long time to do the compilation. Okay. Now the make file now does this additional step, which is to run the Burdock bootstrapper. And what that will do is it will look at the jar file. So remember, SBT is constructing a fat jar with all the dependencies. It's about 14 megabytes. The later step is to convert that into an executable called tube. But in between, what we're going to do is tell the bootstrapper to go and look at all of the contents of that jar file to see what is available on the internet that can be removed. You need to tell it where to look. It can't just search the entire internet for files with the right hash. But what it can do is look through the Maven directories on your system. So when I run this make file, it will do some work. It will download dependencies that you give it. And if I now look at tube, it is 292K. Yeah. If I look at tube now, it's 292K. Now, I can send you that 292K file, and you can run it. It's actually available on in the repository if you want to download it and try. We tried it earlier and it didn't work for some reason, but I've tried it on macOS. I've tried it on Linux. It's had testing on two. There's 2 data points for you, or 3 data points. One of them didn't work, but 2 of them worked, and it's small. 292K seems small even to me, and that is a runnable file. It runs as a daemon. It runs fast. It gives you tab completions. Everything is built in, and everything that's not built in will be downloaded automatically from Maven in order to run it. And if you were to have a whole suite of different command line tools written in Scala with Soundness, which had similar dependencies, then you could distribute them as 300K or similar sized files, and they would reuse the dependencies. They're all stored on my hard disk as hashes that can be reused as necessary. So that is a prospect maybe for future development of in Scala. Command line applications have not historically been something that Scala has been good at or used for reasons that I think are well known and that are almost entirely fixed here. And they're fixed with a system, Soundness, an ecosystem that provides a whole variety of different facilities for doing quite varied things. You saw geolocations, you saw error handling, generic derivation, all of it built only for Scala 3, using all of the features of Scala 3. And probably even experienced Scala developers here will have looked at that code and thought, a lot of this doesn't look like Scala I'm familiar with. But I hope, even if it didn't look familiar, it was easy to read and understand and know, just from looking at it, or make an educated guess at least, what it was doing. And it's quite a small educational gap to go from being able to read something that you basically understand by looking at it to being able to code it. So yeah, I hope this can start perhaps a new wave of development of command line tools. And I would encourage you to have a look at the Soundness website. I've shown you probably about 50 different libraries in some very small capacity at different points today. All of them are available to use in isolation, or isolation plus a few dependencies usually. You don't have to go all in with Soundness. Nick has started using Wisteria for generic derivation, and you've maybe touched on 1 or 2 other libraries, but you've been able to just pick one and focus on that without having to adopt everything I've done. The same is true of the other libraries, and they've been designed in particular to work in isolation, but I don't want to use the word synergistically, but let's say with modularity to work together. So one example of this is there's an HTTP library and there's a JSON library. And you can read HTTP requests as JSON. And that is possible without the JSON library or the HTTP library knowing anything about each other, because they've been carefully designed with type classes such that we anticipate the need of certain things to work together and define those type classes in advance. So they share a dependency deep down the tree. But if you adopt the JSON library, there's no requirement to adopt the HTTP library. They are independent as much as possible. Of those 50 libraries, about 20 have been published with some documentation on the Soundness website. Those are the ones that are sort of more complete and more ready. Others I'm working through. They are working sufficiently well for me to build something like that. But I wouldn't be confident to say they're not going to change in the coming year. So we're approaching stability, but still working on it. Questions, please go to Discord. I mean, you can ask me questions now, but if you have questions later, go to Discord. The link is on the Soundness website. So if you remember soundness.dev, find the Discord link there, along with SPT dependencies and documentation. And I'm going to be available and happy to answer any questions, and very enthusiastic if somebody wants to try something out. And if you've enjoyed the exploration of Scala 3 and you're interested in learning more about Scala 3, I'm offering training, Next Generation Scala, which is an exploration of what is possible in Scala 3. It's a 2-day course that covers, there's some element of bespoke possibilities with the course if you have particular requirements for a company training. But if you're an individual, I will publish some dates later where we will run an online course, either as two full days or a series of evenings where you can just do 2 or 3 hours in an evening over the course of a couple of weeks and learn a lot of things about Scala 3. Learn what's possible. Give yourself reasons why, or learn the reasons why Scala 3 is something you should really be enthusiastic about adopting, and understand how you can use it in your own projects and take advantage of the new features. And I think this talk contrasts a little bit with Nick's talk, because he was moving from an existing working Scala 2 code base. Can I say how large it is? You told me earlier.
I said it in the presentation, 90,000 lines.
90,000, I don't want to give away company secrets. 90,000 lines of code. So like a large amount of code for one person to work on, to do a conversion. I'm building something in 250 lines of code as a greenfield project. It's a very different experience. I think you hit lots of problems because you had stuff that worked and you didn't have complete and full understanding of everything and you needed to make it work. I arrived with nothing existing before and I built everything incrementally. And the experience is very different. So I think both are useful things to understand. But if you're starting new projects, Scala 3 can be a whole lot easier than doing a conversion. So follow me on Twitter if you're not already, and I will make some announcements about training dates when they become available. But if you're interested in company training, perhaps please get in touch, and I'd be happy to look at things to be more interesting and more appropriate for a company training. Maybe just 1 day, maybe 3 days. These are all possibilities. And I think I can open up to questions now. I don't think I had anything else to say. So thanks for listening. Thanks for staying so late.